We've learned two big ideas in calculus so far, and that's limits and differentiation. We're going to go back and talk about limits a little bit more again using L'Hopital's rule. Previously, when we were talking about limits, we had a couple of different techniques that we could use to find a limit. We had the numerical method, meaning we created a table and plugged in values as it got closer and closer to our limiting value. We could look at something graphically and try and interpret what was going on with the limit graphically. And then we had some sort of an analytical approach. Now the analytical approach was something like using some algebraic procedures to simplify until we could find a limit. Now previously, when we would get an answer for a limit after we plugged directly in, we'd get something like 0 over 0. We would call this indeterminate. And we got this indeterminate answer, we would say, okay, we have to do some more work. I don't know what the answer is. And the more work that we could do was a numerical, graphical, or analytical approach. Now we are going to be introduced to a new idea here called L'Hopital's rule. Now L'Hopital was a French mathematician. He was also a French nobleman, and he was very gifted mathematically. However, he wasn't quite as famous as many of the other mathematicians of his age. So he ended up paying another mathematician 300 pounds in like 1690 something, which is probably worth anywhere up to about $7 million or 7 million pounds today, to basically quit publishing his work and give it to L'Hopital first, and then L'Hopital would publish it as his work. So he was kind of a plagiarizer, but he did a lot of good things too, but that's kind of an interesting story about him. And the mathematician that he paid to do a lot of this work was Johann Bernoulli, who came from a famous mathematical family that used all sorts of different areas of calculus and statistics as kind of their background. So kind of interesting story about L'Hopital. Let's go ahead and look at a limit that we're familiar with. Let's look at the limit as x approaches 0 of sine x over x. This is a limit that we worked with earlier. When we plug directly in, which should always be the first step when we're taking a limit, we get 0 over 0. Now 0 over 0 is an indeterminate form, but now not only is it an indeterminate form, but it's called an indeterminate L'Hopital form. Now an indeterminate L'Hopital form means I can actually apply L'Hopital's rule. Now we haven't really talked about what L'Hopital's rule is yet, so let's go ahead and look at that now. L'Hopital's rule says, and we'll write this out formally, I can take, if I get this indeterminate form, and there's other indeterminate forms that we'll look at as well, I can take the limit then of the derivative of the top and the derivative of the bottom and try and take the limit again. The derivative of the sine of x is the cosine of x. The derivative of x is 1. Now when I take the limit, the cosine of 0 is 1, 1 over 1 is 1, which is what we know this limit to be from our previous work earlier on in Calc 1. So this rule that we used here, L'Hopital's rule, basically said, okay, take the derivative of the top over the derivative of the bottom. So I guess we could write that out a little bit more formally if we wanted. So we could take the derivative with respect to x of the top over the derivative with respect to x of the bottom, which would mean the limit as x approaches 0 of the cosine of x over 1, which is 1 over 1, which of course is 1. So what we just did is not the quotient rule. So L'Hopital's is not the quotient rule. L'Hopital's is in fact this nice little shortcut rule that also allows us to find limits a lot faster than going backward and using a numerical or graphical or analytical approach. So let's go ahead and write up L'Hopital's formally. So suppose, the s with a p hanging from it is suppose, both functions f and g are differentiable And it's important that they're differentiable, because if they weren't, then we couldn't really even work L'Hopital's rule. So suppose f and g are differentiable on an open interval. And when we talk about an open interval, we mean we're using parentheses instead of brackets. And this open interval contains some point A with g prime of x not equal to 0. And we'll see here in a moment why that can equal 0, and basically because g is in our denominator. And g cannot equal 0 on the same interval when x cannot equal a. Now a is our limiting value, but we'll see that in a moment here when we write this out. So if the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, and they're both equal to 0, then what I can say is the limit as x approaches a of f prime of x over, actually let's put this notation over here, g of x equals the limit as x approaches a of f prime of x over g prime of x. Now there's a little bit more to it. And so up above here, when I was taking the limit of this trig ratio, that's basically what happened here, is I took my derivative. Now this is only true provided the limit as x approaches a of f prime of x over g prime of x exists. Meaning I have to get an answer here, like 2 or 4 or negative 12. I can't get infinity or 1 over 0. If that's the case, then what ends up happening is I have to say L'Hopital's doesn't work. So again, provided the limit of the as x approaches a of the derivative exists or is plus or minus infinity, because what ends up happening if it's plus or minus infinity is that we can usually apply another rule, a round of L'Hopital's. The rule that we just talked about applies if x approaches a is replaced with infinite limits as well. So we could do x approaches either plus or minus infinity, or we could also talk about one-sided limits as x approaches a from the left, or if x approaches a from the right. So that's kind of what we're looking at with L'Hopital's. But one other thing I want to add to this are there are different indeterminate L'Hopital forms. So indeterminate L'Hopital forms. They would include 0 over 0, infinity over infinity, negative infinity over negative infinity, a positive infinity over a negative infinity, a negative infinity over a positive infinity. I kind of think you get the idea here. So these are all indeterminate L'Hopital forms. So now before we just said indeterminate do more work because we didn't know L'Hopital's because we didn't know how to take derivatives yet. But now we know how to take derivatives, so we can use this idea of L'Hopital's for shortcuts. So let's go ahead and look at quite a few different problems and just kind of get used to working with L'Hopital's. Now the first thing you should always do when you're finding a limit is to plug directly in, direct substitution into the limit, and then if the limit exists, you're done. You don't even need to apply L'Hopital's. So here we have x squared minus 4 over x minus 2. If we plug directly in, we get 2 squared is 4, 4 minus 4 is 0. 0 over 0 is indeterminate, but now it's more than just indeterminate, and it's indeterminate L'Hopital's. So I can apply L'Hopital's rule, limit as x approaches 2, and I'm just going to write this out a few times, the derivative of the top and the derivative of the bottom. This is not the quotient rule. Okay, and I'll write that down here in a minute just to remind us, this is not the quotient rule. So if we take this limit, we get the limit as x approaches 2 of 2x over 1, and if we plug directly in, I get 4 back for my limit. Now there's several different ways I could have done this same problem. For this problem, I could have factored the x squared minus 4 over x minus 2. So this would have been more analytical. The x minus 2's would cancel. And then when I plug in to take my limit, you can see then that I would end up with 2 plus 2 or 4. Okay, but I always have to plug in first to figure out what's going on, and then from there I can either apply the L'Hopital's or I could even apply this analytical approach. So again, there's more than one way to do many of these problems, and it's up to you to show your work and your thought process about the method that you chose. Now when we get into Calc 2 and we learn some more about exponential and transcendental type functions, L'Hopital's really comes in handy for those types. Let's go ahead and look at another limit. Let's do the limit as x approaches infinity on this one. And let's do 4x squared minus 2x plus 1 all over 3x squared minus 1. Again, first thing you should do is plug directly in and figure out if I can use L'Hopital's. So for my previous experience on a problem like this, when we plug directly in, I get 4 times infinity squared minus 2 times infinity plus 1 would be a degree of infinity. And the denominator would also be a degree of infinity. Well, infinity over infinity is indeterminate L'Hopital's. So that means I can actually apply L'Hopital's. Let's go ahead and write out the definition. The derivative with respect to x, 4x squared minus 2x plus 1. And again, this is not the quotient rule. I'm just taking the derivative of the top and bottom separately. This would end up being the limit as x approaches infinity of 8x minus 2 over 6x. If I plug directly in, I get infinity over infinity again, which is indeterminate L'Hopital's. Now in your handwritten homework or on a test, you really need to be sure that you write these out. You need to show that you have indeterminate L'Hopital's. So next step, we take the limit as x approaches infinity of the derivative of the top, 8x minus 2, over the derivative of the bottom, 6x. So this simplifies to the limit as x approaches infinity of 8 over 6, which reduces to 4/3. So there's my limit. Now we did learn some shortcut rules, if you'll recall, earlier in the semester. So let's go ahead and recall our shortcut rules. Now these shortcut rules apply for limits as x approaches plus or minus infinity. So our first shortcut rule was if the degree in the numerator was equal to the degree in the denominator, then the limit is the ratio of the leading coefficients. Now that's a lot easier if I can remember this shortcut rule than using L'Hopital's or any other rule. So if I come back, you can see the degree in the numerator is 2 for both top and bottom. So the limit is the ratio of the leading coefficients. The leading coefficients are 4 and 3, so my limit is 4/3. So to me, if I knew the shortcut rule, that would be a lot faster, but you can also apply L'Hopital's. What if the degree in the numerator is less than the degree in the denominator? If the degree in the numerator was less than the degree in the denominator, the limit is 0. And we went through and did quite a few of these problems and established these earlier on. And what if the degree in the numerator is greater than the degree in the denominator? The limit is going toward infinity or negative infinity. Depending on the problem. So it's going toward either plus or minus infinity. And so therefore, the limit does not exist. Okay, so shortcut rules, important to remember, very handy to be able to recall, and sometimes they can make our work quite a bit easier than going through the whole L'Hopital's thing. So we have these indeterminate forms, and when we have the indeterminate L'Hopital forms, I can apply L'Hopital's rule. However, if I find another approach that I'd like to take, I don't have to apply L'Hopital's. So a couple of notes. L'Hopital's is not the quotient rule. Remember when we take the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared? That's not what L'Hopital's is. It's a straight derivative of the top over the straight derivative of the bottom. Now recall also that L'Hopital's can be used for one-sided limits. It doesn't have to be approaching from the right and the left. I could approach from either one. Also, L'Hopital's only applies if all limits exist, meaning I can't get a 1 over 0 and then say because of L'Hopital's the limit does not exist. That means I have to go back through and I have to establish what the limit is in some other way. So these are a few important things to remember about L'Hopital's. Let's go ahead and work a few more problems. I think for our next problem we can't work transcendental functions yet, so I have to be careful that we don't throw any exponential functions in. Let's go ahead and throw something in with a radical. Let's look at the limit as x approaches infinity of the square root of 9 plus 3x minus 3 all over x. Okay, this minus 3 is not under the radical. So if we plug infinity directly in, what ends up happening here, actually let's just do 0 for our limiting value. If we plug 0 directly in, I'll have the square root of 9 is 3, 3 minus 3 is 0, 0 over 0 is indeterminate, and on a homework or a test you have to justify L'Hopital's at every step. So then my next step would be to take the derivative. So I take the derivative with respect to x, and I'm going to go ahead and rewrite this. I'm going to get it ready to take its derivative over the derivative of the denominator. Remember, this is not the quotient rule. So when we take these derivatives, the derivative of the bottom is the easy one here. The derivative of x is 1. The derivative of a negative 3 is 0, so I just need the derivative of this piece now, which would be bring the chain rule down. So 1/2 9 plus 3x to the negative 1/2 times the derivative of 9 plus 3x, which is 3. So I still haven't taken the derivative. If I do take that derivative, I end up with 3 over 2 square roots of 9 plus 3x. And that's just a simplification. So when I take that limit, the limit of my constant in the numerator is 3. And then in my denominator, when I look through here, I have my derivative, and I plug 0 in. 3 times 0 is 0. 9 plus 0 is 9. Square root of 9 is 3. And I get 3/6 here, which of course reduces to 1/2. So you can use these with radical expressions as well. Sometimes with radical expressions you get caught in this loop that the derivatives get worse and worse and worse, and L'Hopital's actually doesn't work. It's more work than it's worth. It's easier to find a different way to find the limit. Now you can keep using multiple steps with L'Hopital's over and over again, as long as you can establish that at every step L'Hopital still applies. Let's go ahead and look at a trig function. Let's look at the limit as x approaches 0. And we don't always have to approach 0. It seems like in a lot of our problems we are. Let's go ahead and look at secant x minus 1 all over x squared. A couple of things I want you to notice. Always put parentheses around the arguments of your trig functions. So x is the argument, not x minus 1. And we plug directly in. Well, the denominator is easy enough, it's 0. Secant of 0, well, that's 1 over cosine. Cosine of 0 is 1, 1 over 1 is 1, 1 minus 1 is 0, so here I have my nice little indeterminate L'Hopital's. So I go ahead and take the derivative of the top. The derivative of secant x is secant x tangent x. The derivative of minus 1 is 0, and the derivative of x squared is 2x. Let's go ahead and take our limit again. Secant of 0 is 1, and that's something you should know from your trig ratios and also from knowing your unit circle. Same with tangent of 0 is 0. So I get 0 over 0, and I need to establish again that this is indeterminate L'Hopital's. I go ahead and take my derivatives. This derivative is going to be the product rule, so I have the first times the derivative of tangent, which is secant squared, plus the second function, which is tangent, times the derivative of secant, which is secant x tangent x. So I have a nice product rule there. And the derivative of 2x is 2. Now when I take my limit, I have just a 2 in the denominator. And in my numerator, this whole piece will go to 0 because the tangent of 0 is 0. And over here, the secant of 0, we've already set up here earlier, was 1. So I get 1 times 1 squared is 1. So my limit is 1/2. So sometimes you're going to use multiple iterations of L'Hopital's, but at each stage you have to establish that L'Hopital's is still appropriate to use. So for our next problem, let's go ahead and have some limits at infinity. Let's do the limit as x approaches infinity. Let's use polynomial top and bottom. 3x cubed plus 2x squared minus x plus 1 all over x plus 3. So if we take our limit to get started, well, first of all, let's think about this. This is our shortcut rule. The degree in the numerator is greater than the degree in the denominator, so this is going to equal infinity, therefore the limit does not exist. Now I can't just say it equals infinity, I need to say why this equals infinity. And remember, this is because the degree in the numerator is greater than the degree in the denominator. You have to have this justification. So I already know this limit doesn't exist, but let's say I didn't know that, and I decided to try L'Hopital's. Now another way you could establish this limit is to divide through by the highest power of the exponent in the denominator. So that's another approach. So if I plug directly in, I'd get infinity over infinity, which is an indeterminate L'Hopital's form. And then I'd start taking my derivatives. So I'd have 9x squared plus 4x minus 1 all over 1. Now when I take my limit, in the numerator I get infinity, and of course in the denominator I have over 1. This is not, I'm going to put this in red, it's so important. So this is not indeterminate L'Hopital's form. Therefore, no conclusion. I have to stop. I just quit right there. No conclusion. I have to find another way to determine the limit. So the other way that we could use then would be right back up here. Now you might look at this and say, well, we got infinity up here, so why can't I use this infinity down here? That's not always going to happen. That's not anything I can depend upon. So you're going to run across a problem, probably on your homeworks or your handwritten homework or your test, that's going to run into this situation, and you better be looking for it and be ready for it, because not every problem we should go blindly into assuming that we can apply L'Hopital's over and over again. Sometimes it's not appropriate, and we have to know when it's not appropriate, and we need to know other ways that we can solve for that limit. And just because they're fun, let's do another trig limit. Now the limits that we're looking at and the rule that we're looking at again was actually established by Bernoulli. So Bernoulli showed L'Hopital how this works, and then L'Hopital had of course paid him to not publish his work so he could publish it under his name. So it's interesting that L'Hopital's got to keep the name of this rule instead of it going to Bernoulli, but sometimes that's what happens. So let's go ahead and look at some trig functions. Let's look at 6 sine 9 pi x over cosine pi x plus x. Now notice the plus x is not part of the limit. Let's go ahead and plug directly in. So if I plug in 1 for x, I get the sine of 9 pi, which is 0. 6 times 0 is 0. Over here, when I plug directly in, I get the cosine of pi, which is -1. -1 plus 1 is 0. 0 over 0 is indeterminate L'Hopital's. So I can start by taking my derivatives. Now I'm just going to drag the 6 along. The derivative of the sine of an argument is the cosine of the argument times the derivative of the argument, which in this case is 9 pi. The denominator, the derivative of the cosine of u, cosine of the argument, is negative cosine argument prime. And the derivative of x, of course, is 1. I want to rewrite this. So I have 6 times 9 is 54 pi times the cosine of 9 pi x all over negative pi cosine. That's not right. The derivative of the cosine is sine. This should be a sine right here. So let's make sure we fix that up. Negative pi sine pi x plus 1. So let's go ahead and plug directly in again. So this is a 1. Cosine of 9 pi, remember x is equal to 1, so 9 pi would be a reference angle of like cosine of pi. So this would be a negative 1, so this would be a negative 54 pi in my numerator. And let's see our denominator. As I approach 1, sine of pi, of course, is 0. So this whole term goes to 0. 0 plus 1 is 1. And so I'm left with my limit is equal to negative 54 pi. So knowing your trig functions, trig ratios, trig derivatives, and your unit circle is going to be very important to be successful on these types of problems. Now there's other indeterminate forms out there, but they're not indeterminate L'hopital. So let's go ahead and look at other indeterminate forms. Now we're only going to focus on 2 of these indeterminate forms in this section because we haven't learned about exponential and logarithmic, also known as transcendental type of functions in calculus yet. So these other indeterminate forms really don't come up a lot yet, but they will once we learn those in Calc 2. So the 2 indeterminate forms I want to look at are 0 times infinity and infinity minus infinity. So you'd think, well, 0 times infinity should be 0, because 0 times anything is 0. And you'd think infinity minus infinity would be 0 because, you know, anything subtracted from itself is 0. But remember, we don't know what degree infinity either one of these is. And also, this is not an arithmetic operation. This is the results from taking a limit. So these are called indeterminate forms. Now, when I get one of these indeterminate forms, what I like to do is I like to rewrite them into an expression where I can get an indeterminate L'Hopital's. So if I get one of these indeterminate forms, my rule is to rewrite. And a lot of times when I think about rewriting these, I rewrite as a fraction, as a single fraction. So not all the time, but a lot of times as a single fraction. Take the limit again, and hopefully when I take the limit again, I'll get indeterminate L'Hopital's. If I don't, that means I need to keep rewriting or find another way to do the problem. Now there's a few other forms that we run across that really look indeterminate, but they're actually not. So let's go ahead and look at those as well. A couple of these would be something like, what about, we talked about 0 times infinity. What about infinity plus infinity? Well, infinity plus infinity is just another infinity. So if you get a limit where you get infinity plus infinity, your answer would be infinity, which of course does not exist for a limit. Let's look at negative infinity minus infinity. This is just equal to another degree of a negative infinity. 0 to the infinity is equal to 0. And 0 to the negative infinity is equal to infinity. Now these are all limits. So these are not indeterminate forms. These are interesting limit results. So if you get these forms, they actually have a solution. Some of the solutions means the limit does not exist, and some of them actually mean the limit does exist. But these are some that you might come across. Maybe not so much in Calc 1, but in Calc 2. So let's look at some problems where we'll run across these other types, and then we'll try and rewrite them. So let's go ahead and look at a problem, trig function. Let's do a trig function. Let's look at the limit as x approaches infinity. Let's use x cubed over 7 times, we're going to make this a little bit ugly if we can, minus sine of 6 over x. Okay, again, the first thing we should do is to plug directly in, and if we do that, for this first piece, we definitely get infinity cubed over 7, which is infinity. I can't make infinity signs like a sideways 8. This piece, as I go toward infinity, 6 over infinity goes to 0, minus 6 over infinity goes to 0. The sign of 0 is 0. So this ends up looking like infinity times 0. So this is an indeterminate form, but it's not an indeterminate L'hopital. So this is indeterminate. Do more work. And the way I want to do this more work is to rewrite this. Okay, so let's go ahead and try and think about how we could rewrite this. Well, usually if we're going to get an indeterminate form such as infinity over infinity or 0 over 0, I need a clear numerator and a clear denominator. So to start with, I would like to rewrite this as my numerator. Now somehow I want to rewrite this first piece, x cubed over 7, as my denominator. And if I think about it, I'm multiplying by x cubed over 7, which is the same as dividing by 7 over x cubed. Because remember, when you divide by a fraction, you multiply by the reciprocal. So now, when I take my limit, let's see what we get. As x approaches infinity, and this is a pretty common approach to take here for the indeterminate form 0 times infinity. As x approaches infinity, 6 over infinity goes to 0. This piece, 6 over infinity goes to 0, sine of 0 is 0. This bottom piece is also going to 0. 0 over 0 is indeterminate L'hopitals. Now I can apply L'hopital's rule. These derivatives might be a little bit ugly, so I'm not sure if I want to apply L'hopital's rule, but I'm going to. Okay, so let's go ahead and give this a shot. So, the derivative of 6 over x. I'd flip the x up top and rewrite this as 6x to the negative 1, which would be a negative 6x to the negative 2. The derivative of a negative sign is a negative cosine of u times the derivative of u. And we just took the derivative of 6 over x, so we know what that is. Now this piece I can rewrite as 7x to the negative 3. So when I take the derivative, I get negative 21x to the negative 4. You decrease the exponent by 1, so negative 3 moves down to negative 4. Now this is just ugly. I don't think we improved our situation here. But let's keep working with it to see what we can come up with. Now if we wanted to, we could have done a substitution here, and I'll show you what that substitution looks like. But for now, let's keep just plugging away through this. Let's look at the limit as x approaches infinity. And I see that I have this in common, this negative 6x to the negative 2 I could factor out, and I'd be left with 1 minus the cosine of 6 over x. And of course this is all over negative 21x to the negative 4. So this bit right here I can simplify. So if we simplify this, I have a negative divided by a negative is a positive. 6 over 21. Okay, so I'm not taking a limit yet. I'm just simplifying this. 6 over 21, they're both divisible by 3. 6 divided by 3 is 2. 21 divided by 3 is 7. And then I'm going to flip this negative 4 up top and it becomes a positive 4. Flip the negative 2 into the bottom and it becomes a positive 2 in my exponent. So I have x to the 4th over x squared, which leaves me with an x squared on top. And this of course is times 1 minus cosine of 6 over x. So when I take my limit again, I definitely have an infinity here. And oh geez, look at this. As x goes to infinity, 6 over infinity goes to 0, and the cosine of 0 is 1. 1 minus 1 is 0 over 7. So this is infinity times 0 again. So I just undid all the good that I did. So up here I had an indeterminate L'hopital's form, and then I worked through this. and I got an indeterminate form, so L'Hopitals cannot be applied again. I'd have to rewrite this somehow again. So I could go back through and say, well, let's use the old trick I had. And I'm going to rewrite this as 1 minus cosine as 6 over x divided by 7 over 2x squared, and take my limit. As this goes to infinity, I have my 6 over x goes to 0. Cosine of 0 is 1. 1 minus 1 is 0. And this denominator, 7 over 2x squared, as x goes to infinity, goes to 0. So this is 0 over 0 indeterminate L'Hopitals. So I think, okay, well, I'll apply L'Hopitals again. So remember, this, I couldn't apply L'Hopitals. I had to rewrite this in some other way in order for me to get going again. So I had to rewrite. So I don't want you to think that this was a direct outcome from here. I had to rewrite this first to get it into an indeterminate L'Hopitals form. The derivative of 1 is 0. The derivative of a negative cosine, derivative of cosine is a negative sign, and I already have a negative sign out front. So this is going to be a positive sine 6 over x times the derivative of 6 over x, which is negative 6 over x squared. And we established that up here, so it's the same thing. Okay, now down here, when I take the derivative of 7 over 2x squared, I can think about this as 7 halves x to the negative 2. I'd bring the negative 2 down, the 2's would cancel, so I have negative 7x to the negative 3. Now I'm not taking the limit, I'm just rewriting this. And you can kind of see I'm getting in this little vicious circle. I keep getting to this indeterminate form that's not an indeterminate L'Hopitals, but let's see if we can clear that up. Negative divided by negative is a positive, so I have this 6 over 7 that I could pull out front. Then let's figure out these x squareds. This would be the same as negative 6x to the negative 2, so this would flip into the bottom. The x cubed would flip into the top, and they'd cancel, and I'd be left with an x over here. So now, as I'm working, I don't like this one at all. I don't like how this is turning out. Now, 6 over infinity is going to 0. The sign of 0 is 0. So I have 6/7 times 0 times infinity. Dang it! So this is another indeterminate form that L'Hopitals cannot be applied. Okay, so I'm kind of getting to a point here that I think that I'm going to give up on this approach I'm taking and try and find something new, but let's just try it one more time. So I'm going to rewrite it. I'm going to take the limit as x approaches infinity, and I'm going to try and rewrite this. I have a 6 over 7. Oh, I have this x, so let's write it like this. Let's do sine 6 over x, and then this bit, 6x over 7, would be the same as 7 over 6x if I divided by the fraction. If I take my limit, I get 0 over 0. Now I'm back on track to indeterminate L'Hopitals, but I just don't think this is going to get me anywhere. So let's go ahead and take derivatives and check it out. Limit as x approaches infinity. The derivative of the sine of x is the cosine of the argument times the derivative of the argument. This looks familiar. This is not good. Now here, if we rewrote this as 7/6x to the negative 1, I'd bring the negative out front, decrease the exponent by 1. So I'm not taking a limit, I'm just rewriting this. 6 over x. And then I have a negative divided by a negative, which is a positive. So that would be a 6 and a 7. Now this x to the negative 2 I could rewrite as negative 6x to the negative 2. Oh my gosh, this is good news. This is going to cancel. The x to the negative 2's will cancel. And as the x to the negative 2's cancel, looks like I have one more 6 in here though. That would flip up top. So I'd have a 36 out front. And I'm ready to take my limit then. So I'm going to rewrite just real quick. The limit as x approaches infinity of 36 cosine 6 over x all over 7. So now as I finally take my limit, I really hope that I get a solution here and not just another indeterminate form. The cosine of 6 over x, as x goes to infinity, 6 over x goes to 0. The cosine of 0 is 1. Oh good. 36 over 7 times 1 is 36 over 7. There's my solution. I didn't think it was going to work out. I thought we were going to get caught in one of these recursive where I keep getting back to the original, but that didn't happen, thank goodness. But we did have to stick after this and very, confidently take derivatives till we got to our solution. There could have been a faster way. This was a little bit lengthy as I'm scrolling up here to even see what the original was. Here's the original. I wonder if we could have done this a little different. I noticed that we have 6 over x and 6 over x. I wonder if we could have made a substitution. So I'm going to look at this same problem just a little different. See if I can copy that. I don't want to import it. Copy. Okay, so same problem. Just want to see if there's a faster way I can do this. The other one was pretty fun though. It was pretty suspenseful to see what we get at the end. So same problem, different approach. Hopefully shorter. So let's make a substitution. So for this one, let's do a substitution. Let's let t equal 1 over x. Now the reason we want to look at t equal 1 over x, then the limit as x approaches infinity of 1 over x is going to be equal to 0. So the limit, and again we're talking about t here, so this limit as x approaches infinity of t is equal to 0, just by substitution. So let's go ahead and rewrite this. This would be the limit as t, because if we look at this and we're thinking x is approaching infinity, as x approaches infinity of this expression, t was going towards 0. And we're only approaching from the right. Let's go ahead and have a look real quick. 1 over x. Here's the graph of 1 over x. So when we're talking about approaching t, so t is approaching 0 from the right, if you notice this is going toward infinity, so I'm approaching from the right. So let's go ahead and rewrite this expression and to see if we can get this into some sort of a form where we have an indeterminate L'Hopital's right away and it's easier to take the limit. Now we're trying to rewrite this, so the limit as t approaches 0 from the right. So 6 over x would be the same as 6t, because remember t was 1 over x, minus sine of 6t, and this would all be over, okay, so x cubed over 7, if I flip that, would be 7 over x cubed, which would be 7t cubed. Okay, so if you have to run through that algebraically to show that, you can. Now when I take my limit, I get 0 minus 0, which is 0. 0 over 0 is an indeterminate L'Hopital's. So again, same problem using substitution. So same problem. I don't want you to think this is a continuation of what we did above. This is the same problem, different approach. Okay, so now that I can use L'Hopital's, I'll take the limit as t approaches 0 from the right. The derivative of 6t is 6. The derivative of a negative sine of 6t is a minus 6 cosine of 6t all over 21t squared. If I take my limit again, I get 6 minus 6, which is 0. 0 over 0 is another indeterminate L'Hopital's. Let's take a limit as t approaches 0 from the right of our derivatives. The derivative of 6 is 0. The derivative of a negative 6 cosine 6t, the derivative of the cosine is a negative sign. Negative times a negative is a positive. This is going to be a 36 sine of 6t all over 42t. Now the reason that this is a 36 is because when I take the derivative of 6t I get another 6. 6 times this 6 is 36. Let's go ahead and take the limit again, and I get 0 over 0, which is an indeterminate L'hopital's. And we should be almost done with this, because when I take my another set of derivatives, what ends up happening is this is going to finally go to a constant. The derivative of 36 sine 6t is going to be 216 cosine of 6t all over 42. Now the 216 comes into play when I take the derivative of 6t. I get 6. 6 times 36 is 216. So when I take the derivative or the limit as t approaches 0, the cosine of 0 is 1, and I'm left with 216 over 42, which reduces to what? 108 over 21. These are both divisible by 3, and I end up with 36 over 7. So there are so many different ways that we can rewrite this. Again, different approach. Sometimes the first approach I took to this was kind of leading us to a path where it didn't seem like I was getting anywhere, but I stuck with it and it did come out okay. But that won't always happen with problems. A lot of times with radicals involved, you get to a point where you really can't work any further. It's getting worse instead of better, and I have to use a different approach. So you could run into problems like that. Now on the test, a lot of times I'll give you a problem that I've already worked with L'hopital's and then ask you to find or verify whether it's accurate or not. And if it is accurate, you know, state that it is and why, and if it's inaccurate, find the mistake. So that's another thing that we can do. Instead of just working the problems, you could be looking at problems that are already worked and trying to find any errors. I know one of the fun problems that you have in your homework set is kind of complicated, but I want to help you out with it a little bit. They ask you to establish one of the limits found in L'hopital's book that he wrote, his calculus book that he wrote in 1700 or near 1700, which was probably Bernoulli's work anyway. But I want to give you a start on it. It's basically, I'll do this in a different color. It's basically taking the limit as x approaches a, and this is the complicated part, is there's no number here. They just are using variables, and they're using this expression 2a cubed x minus x to the fourth minus a, and again this is the problem as it appeared in the text, a squared x all over a minus the fourth root of a x cubed. And what they tell us here is a is greater than or equal to 0. So a is positive, basically, or 0. So I want to find this limit. I want to find this limit and establish L'hopital's. But one of the things that makes this problem difficult is the a and the x business. Which is constant, which is variable. So just to get started, I would like you to note that a is constant. That means it's a number. And if you take the derivative of a number, like the derivative of 6 is 0, the derivative of a will be 0. X is the variable. And this is what you're taking the derivative with respect to. So let's go ahead and get started on this problem. This is just a fun problem. So I guess if you watch the lecture, it's a bonus that you'll find out what the solution to this homework problem is. So if we take the limit as x approaches a, this value right here turns into an a. So I end up with 2a to the fourth minus, again, x turns into an a to the fourth square root, minus a times the cubic root of a squared times a all over a minus the fourth root of a times a cubed. So let's see what this looks like. 2a to the fourth minus a to the fourth is the square root of a to the fourth. Let's see what we have over here. a squared times a is a cubed. The cubic root of a cubed is going to be a. A times a is a squared. And in the bottom, I have a cubed times a is a to the fourth root of a to the fourth is a. And of course, the square root of a to the fourth is a squared. So this is 0 over 0, or indeterminate L'Hopitals. So again, everywhere there's an x, basically I'm plugging in an a. So in order to apply L'Hopitals here, I need to take some derivatives, and it's a little bit intimidating, but let's work through it. So for this piece, I'm going to use the chain rule. I'll bring the 1/2 down, decrease the exponent by 1, so I get a negative 1/2 here, and then I'm going to multiply it by the derivative within. So 2a cubed is all just constant. X is my variable. So the derivative of 2a cubed x is just 2a cubed. The derivative of minus x to the fourth is minus 4x cubed. So there's the derivative of my first piece. Now the second piece. This second piece I'm going to break up into two parts. I have this a that's a constant that I'm going to drag along. I also have this cubic root of a squared that I'm going to drag along because it's a constant. And that leaves me with the cubic root of x. So the derivative of the cubic root of x is 1/3 x to the negative 2/3. Again, if you want to hit pause and verify this, that would be a great idea because this is a tough problem. Okay, now the derivative of a, the derivative of a constant is 0 in my denominator. Now over here, I'm going to subtract off the 4th root of a. Okay, and then I'm left with the 4th root of x cubed. So that would be x to the 3/4. So I'd bring the 3/4 down, decrease the exponent by 1. So I end up with 3/4 x to the negative 1/4. So this is my derivative. I don't want to take the limit now, I want to simplify. So again, I'm not taking a limit, I'm just simplifying here. Okay, so it looks like to me for this piece, this would flip down into a denominator. So this is going to be the square root of 2a cubed x minus x to the fourth. And then this half gets multiplied by 2a cubed to give us an a cubed. And the half of a negative 4x cubed is a negative 2x cubed. So that's how that first simplifies. And then it flips down into the denominator. Okay, now this piece over here, let's see what's going on. I have an a to the 2/3 times a to the first, so that would be a to the 3/3 times a to the 2/3 is a to the 5/3. And then this flips down as a 3x to the 2/3 into the denominator. Okay, and this is all over. Okay, I have a negative sign in the denominator. And this is the 4th root of a. The 3 stays up top, so this is 3 times the 4th root of a all over 4x to the 1/4. Now this doesn't look any simpler, but it is. I'm actually going to take my limit right now. So as we take the limit, the x's are turning into a's. So here I have an a cubed minus, this x is approaching a, so minus 2a cubed. Okay, in my radical, I have 2a cubed x, but x is approaching a, so I have a cubed times a is a to the fourth, so I have 2a to the fourth minus a to the fourth, because again, x is approaching a, minus, let's see what we have here, a to the 5/3 divided by a to the 2/3, because remember x is approaching a, would leave me with an a to the 3/3, or just a over 3. A to the 3/3 is the same as a to the first. Now in my denominator, don't forget the negative sign. So I have a 3/4 here basically because this is the 4th root of a, which is the same as a to the 1/4, so they cancel. So a cubed minus 2a cubed would leave me with a negative a cubed. Now over here I have 2a to the fourth minus a to the fourth is a to the fourth. The square root of a to the fourth is a squared. And I have a over 3. And I'm going to go ahead and flip this up top. When you divide by a fraction, you multiply by the reciprocal. So the negative sign stays with it and then it flips. So continuing to simplify, this is a fun little problem. A cubed over a squared is a, so I'm left with negative a minus a over 3. So I'm going to write this as negative a over 1, so I can keep that in fractional form, minus 4 over 3. Okay, finding a common denominator, that would be negative 3a minus a all over 3 times a negative 4/3. Okay, I'm still simplifying. Negative 3a minus a is a negative 4a over 3. It's a 3 times a negative 4/3. Negative times a negative is a positive. 4 times 4 is 16. 3 times 3 is 9. So I'm left with 16/9 a. So that's one of the problems he used in his textbook back in the, I guess, almost 1700 or really close to 1700 to establish the use of L'Hopital's rule. So kind of an interesting problem. It's fun to work. In fact, all of these are fun to work and they can be a challenge, but just remember you always have to establish L'Hopital's before you can move ahead to the next iteration to find the limit. If you can't apply L'Hopital's, you're going to have to find another method like a numerical approach, a graphing approach, or an analytical approach. Good luck on this assignment, and I hope you enjoy working these problems.